Chapter 7, Newton's third law of motion, action and reaction. The big idea: for every force there is an equal and opposite force. Whenever there's a force, there's always another force. They're always in pairs. There's a mutual force that acts together. So when we're talking about forces, remember we said a force was a push or a pull, and when we're talking about a mutual action, we're talking about an interaction between one thing and another thing. So for instance, if you push on the wall pushes back on you. If the hammer hits the nail halts the hammer. So there's always a pair, there's always an interaction between these two things. So the hammer, there must be a force exerted on the hammer to halt its process. That's the nail. And Newton figured that if the hammer exerts a force on the nail, then the nail must be the one exerting the force back on the hammer. There's always those pairs of interactions between the two things. Alright, so here's a question. Does a stick of dynamite contain force? And the answer is no. Force, there's no push or pull in there. There's nothing like that. Forces are interactions, remember. A stick of dynamite would contain energy. That energy could then be changed into a force, but as just a stick of dynamite, it does not contain force. Alright, Newton's third law. This one states that one object exerts force on a second object exerts a force, an equal and opposite force on the first object. Or, in other words, for every action, there's an equal and opposite reaction. So we've got an action force, we've got a reaction force. You cannot have one force without the other. They are always together. They are always equal, and they are always opposite, and they always occur at the same time. So you should always be able to figure out if there's this one force, what's the other force? There's always an interaction force. Okay, so there's always an action, there's always a reaction that goes along with it. So for instance, let's talk about a couple examples. If you push against the floor pushes against you. If the tires of a car interact with the road push on the road pushes on the tires at the same time. When you're swimming, you push the water backwards, the water pushes you forward with equal force. And in order for these interactions to occur, we have to have friction. If you're trying to walk on ice, you may not be able to exert an action force. And if you can't get the action force, you don't get a reaction force, you can't move forward. So you can't get motion without this action-reaction force. So here's this girl, she's jumping out of the boat, and you've probably done something like this before. So she's trying to jump forward, the boat moves backwards. Now, that's not a bad thing if she makes it to the dock, or even if she makes it into the water, it's probably alright. It's when you get halfway that's the real problem. So the dog wags the tail wags the dog. The key here is you always need to figure out what the two interactions are, the two different things are. So we're going to talk about identifying interacting objects, A and B, A acts on B, B acts on A. It may seem kind of simple, and yet sometimes it's hard for you to think about, exactly which one is reacting. Okay, so the simple way to do it is if object A exerts force on object B, the reaction is object B exerts a force on object A. Now, it doesn't really matter which one you consider to be the action force and which one you consider to be the reaction force, but there have to be those pairs of forces. Alright, so here's one that sometimes is a little bit more difficult. If we have a boulder that falls to the earth, we could say the action force is the earth applies a force to the boulder. what's sometimes hard to figure out is, well, what's the reaction force? Well, in this case, the reaction force is that the boulder is applying a force to the earth of equal and opposite magnitude. So whatever the force is on the boulder pulling it down, that boulder is applying the same force on the earth pulling it up. So here's some more examples. Tire pushes on the road. Road pushes on the tire. Okay, these are these are the actions. Action: earth pulls on the ball. Ball pulls on the earth. Reaction: rocket pushes gas. Gas pushes rocket is the reaction. Okay. All right. So we know that the earth pulls on the moon. Does the moon also pull on the earth? And if so, which is stronger? Well, yeah, we know that the earth pulls on the moon, so therefore the moon must pull on the earth. Which one's stronger? Well, they are exactly the same. They're always the same. They're always equal and opposite. Okay? I like, they talk about how, well, that's kind of like saying which is farther to go from New York to San Francisco or from San Francisco to New York. Well, they're always the same. Alright, so let's talk about action-reaction on different masses. So if we have a small mass, we're going to get greater acceleration than if we have a large mass, obviously. So we'll go back to our boulder example. The earth is pulled by the boulder just as much as the boulder is pulled by the earth. But what's the difference? Well, even though the forces are equal and opposite, the boulder falls to the earth, right? Now, technically, the earth actually falls to the boulder, but the distance that the earth moves is far, far less because the size of the boulder compared to the size, or maybe I should say the mass of the boulder compared to the mass of the earth, is so extremely different. And if you think of Newton's second law, F equals ma, the boulder can be accelerated. There can be a force there that accelerated. And the earth, there's a force there, but the acceleration is going to be so much smaller because the earth's mass is so much smaller. So we don't really even notice the earth's accelerations. It's, as they say here, infinitesimally small because the earth is so large compared to the boulder. Alright, so when a cannon is fired, we've got an interaction between the cannon and the cannonball. The force is equal and opposite. And, you always think about, or you've probably seen pictures of how the cannonball goes one way and the cannon recoils, it goes the other way. Now, the cannonball moves so much faster because the cannon is so much larger. And so that's why you have, large cannons with that are very heavy and, massive objects, so that they don't move so far. They're still going to recoil, and if you watch, videos of cannons being shot and so on, you'll see recoil, but the cannonball is going to move so much faster than the cannon because of the mass that it undergoes. Cannon's much smaller, or much bigger, ball is much smaller, so the ball moves a whole lot faster than the cannon. So, we know if we're comparing these, we've got the cannonball, and we're saying that, hey, we've got this force, and notice that on both the cannonball and the cannon, the force is the same size. So they're equal. But the mass on the cannonball, it's the little m, so it's small. And the mass of the cannon, it's a big M, so it's big. Therefore, the cannonball gets big acceleration, big A, and the cannon gets small acceleration, little a. And we can do this same thing. We can extend this on to rocket propulsion. Same idea. Let's talk about it. Start with a balloon. A balloon, has air escaping from it, and the balloon moves upward. If you release the balloon, the air comes out. Those objects are like little cannonballs being shot away from the balloon. The balloon recoils and moves the other way. So, think of a rocket as being just kind of a tiny molecular cannonball shooter, or the gas, the molecules being the cannonball, and the rocket or the balloon is being the cannon, and we get the equal and opposite forces from those two things. A lot of times people believe that rockets are propelled by the impact of exhaust against the atmosphere. Or people think that when a rocket takes off, it's the gases are pushing on the ground, and the ground pushes up on the rocket. Well, if that's the case, then how does a rocket work out in space? And in fact, years and years and years ago, before we knew about it, scientists wondered, can a rocket actually work out in space, or can it just no longer work because there's no air to push against? Well, we know that according to Newton's third law, it does work. You could be out in space and you could just throw a ball. If you have a baseball and you throw it one way, you're going to go the other way. So anytime that something moves out one way, there's an equal and opposite force going the other way. And in fact, rockets actually work better above the atmosphere because we have no air resistance, so they actually go even better. So here's our rocket, space shuttle. Unfortunately, we'll never get to see one of these lift off again. But here's our space shuttle. We've got all of the exhaust gases coming out, and the mass of those times their acceleration provides the force. And whatever force is coming out, that's the force that the rocket moves upward when it goes. So if we think about Newton's third law in an example of a helicopter, the blades spin around, they push air down. That's the downward force. Therefore, the air pushes the helicopter up. That's the upward force. And if we get the blades moving fast enough that we've got more force down than what the helicopter has for weight, and the helicopter lifts up. Birds do the same thing. They force air down, keep the bird up in the air. Alright, think about this. Tug of war occurs between boys and girls on a polished floor that's somewhat slippery. If the boys are wearing socks and the girls are wearing rubber-soled shoes, who will surely win and why? Well, that's not hard to figure out. The girls are going to win. The boys can't put any force of friction on the floor, so they're not going to be able to hold or pull. And the girls would be able to exert a greater force, so the boys would be sliding towards the girls.